Hello everyone, my name is Konstantinos Dimitras, and today I will present our research on the influence of 3D printing parameters on the tensile performance of ASA specimens. This study was carried out at the Laboratory for Advanced Materials, Structures and Digitalization, Department of Aerospace Science and Technology at the National and Kapodistrian University of Athens, in collaboration with Mr. Kostopoulos and under the supervision of Dr. Georgantzinos. Let's start with why we are here. In the aerospace industry, material reliability is critical. We focused our research on ASA. Unlike common plastics like PLA, ASA offers exceptional UV resistance and thermal stability, making it a strong candidate for outdoor aerospace components. However, 3D printing is anisotropic, meaning its strength changes based on how you print it. Our objective was to quantify exactly which printing parameters control the strength and stiffness of ASA so we can use it reliably in engineering. For our methodology, we used fused filament fabrication using a Creality K1C printer. To ensure our results are standardized and comparable to other studies, we strictly followed the ISO 5272 Type 5A standard. We used high-quality ASA filament to ensure consistent material properties throughout the experiment. Here, you can see the cut geometry of our tensile specimen. They were designed with a total length of 75 mm and a thickness of 2 mm, which is optimized for the grippers of our tensile testing machine. The gauge length, the area where the stretching happens, is 20 mm. To analyze the printing process efficiently, we used the Taguchi design of experiment method. There are dozens of printing parameters, but checking all of them would require hundreds of tests. Instead, we selected 5 critical factors: infill angle, build orientation, printing speed, layer height, and nozzle temperature. Using the Taguchi L18 array, we could study the interaction of these 5 factors using only 18 unique experimental runs. This table shows the specific L18 orthogonal array we used. Each row represents a unique combination of parameters. For example, experiment 1 uses a flat orientation with a thin 0.1 mm layer height, while experiment 2 uses an upright orientation with a thicker 0.2 mm layer. We repeated each experiment 5 times, resulting in 90 total specimens. We performed uniaxial tensile tests until failure. On the left, you see the specimen loaded in the machine. On the right, you see the aftermath of the tests. A key observation here was the failure mode. Specimens printed flat tended to stretch and yield ductile fracture, whereas specimens printed upright tended to snap cleanly between the layers, brittle delamination. Now, let's look at the results, starting with elasticity or Young modulus. Our maximum recorded value was approximately 827 megapascals. According to our signal-to-noise analysis, the two most influential factors were printing speed and nozzle temperature. Lower speeds allowed for better material deposition, while higher temperatures improved the fusion between layers. Therefore, if your goal is a stiff part, you should print slowly and hot. Here, you can see the Taguchi main effects plots for Young modulus. On the means plot, look at the steep slope for printing speed and temperature. The data clearly shows a downward trend for speed, meaning as we print faster, the material becomes less stiff. Conversely, the line for temperature goes up, indicating that higher heat improves stiffness. This confirms that allowing the material more time to bond at higher temperatures creates a more rigid internal structure. Moving on to tensile strength, which is often the most critical property for aerospace parts. Here, we observed a massive performance gap driven by build orientation and layer height. The optimized set, flat, achieved a mean strength of 42.21 megapascals. The reference set, upright, only reached 16.12 megapascals. This is 2.6 times difference in strength. Furthermore, the flat samples had much more variability, making them far more reliable for engineering use. This confirms that for load-bearing parts, printing orientation is the single most critical decision. These graphs visually explain that performance gap. If you look at the build orientation factor in the plot, you see a drastic drop-off when moving from flat to upright. This is the steepest line on the entire chart, proving it is the dominant factor. Additionally, looking at layer height, we see that thinner layers, 0.10 mm, result in higher strength. This suggests that thinner layers minimize the air gaps in the part, resulting in a denser, stronger cross-section. In conclusion, the Taguchi method allowed us to successfully optimize the ASA printing process. Our key takeaways for engineers are: for stiffness, prioritize low speed and high temperature. For maximum strength, print flat with low layer heights, 0.10 millimeters. And for ductility, ensure the build orientation aligns with the load vector. These parameters provide a verified baseline for manufacturing reliable ASA components. Looking ahead, we plan to expand the study by investigating environmental factors such as testing at high ambient temperatures, studying different strain rates to simulate impact loads, and developing finite element models to simulate these tests digitally, saving time on future experiments. Thank you very much for your attention.